Energy is one of the most important concepts in physics. Every day, we use it in physics to help us understand the world around us. For example, if you want to know how fast our phone will charge overnight, we're directly or indirectly using energy. But here's the thing, energy doesn't exist in a way you might think. When I say this, I'm not claiming that your teachers have been lying to you. What we're trying to do is clear up a common misunderstanding. Many people imagine energy as some kind of invisible particle that you can hold or touch. But energy isn't like that. Think of energy more like the color of your clothes. Your clothes have color, but color isn't a thing that exists by itself floating around in the universe. It's just a property of the clothes, not something you can take out and examine on its own. Energy is similar. It's a property that things have, but it's not a physical object. So, what exactly is energy? To make this easier to understand, let's imagine a simple scenario. Picture the universe as a small town. You'll see why this makes sense soon, I promise. In this town, there is a magical store where you can trade your money for two items, shoes and cars. Here's the catch. The price of a shoe depends entirely on its height. The taller the shoe, the more expensive it is. And you can tell exactly how much someone spent on our shoes just by looking at their height. The same goes for cars. The faster a car can go, the more money it costs. And you can figure out the price by measuring its speed. Now, you're a citizen of this town, and you walk into this magical store with the intention of buying a fast car. But right at the entrance, there is a sign that reads, "We only accept jewels." You know that jewels can only be earned through work. When you step inside the store, it looks completely empty, no cars, no shoes, but the moment you pay the store 10 jewels, your car suddenly appears, and you can drive off at a speed directly proportional to those 10 jewels you spent. In physics, this concept is called work, meaning the amount of energy required to do something. In real life, if you're pushing an empty shopping cart, it's pretty easy to get it moving. But if the cart is filled with stones, pushing it takes a lot more effort, or in other words, more energy. And the more stones you add, the more work it will take to move the same cart. Going back to our scenario, exchanging your jewels for a tall shoe or a fast car doesn't mean you can never buy anything again, because the store allows trades. Remember, the height of the shoe and the speed of the car in this town are directly proportional to the number of jewels you've paid. And that's the key. If you're not happy with the speed of your car or the height of your shoes, you can swap one for the other. In real life, energy works the same way. You can trade one type of energy for another. Just like in our imaginary town, in the town, shoe height is worth jewels. In reality, the height at which I hold a stone also translates to joules, and we even have a name for it: gravitational potential energy. If I let go of that stone, gravity starts to work on it, making it move. As the height of the stone decreases, the amount of joules invested in gravitational potential energy also decreases. At this point, you might wonder, if the stone's height decreases, am I losing energy? The answer is no. The energy lost in height has been converted into speed, so the total number of joules stays the same. We even have a name for the joules invested in speed: kinetic energy. I mentioned that the amount of joules stays the same, and this brings us to one of the most fundamental laws in all of physics, the law of conservation of energy. To understand what this means, let's go back to our town. Imagine that this town is the only place that exists. There are no other cities, no other universes. In this isolated world, the total number of joules you have, whether invested in shoes or cars, never changes. You can trade them back and forth, but the total stays the same. But now, suppose a stranger suddenly arrives in the town, completely unaware of how it works. He decides to explore and quickly notice something interesting. Some people wear low shoes, others wear high ones, and there are cars, some fast, some slow. He also notices the sign on the shop door that says it only accepts jewels, so he decides to go inside. After learning that the shop sells cars and shoes, and that their prices are all measured in jewels, just like everything in the town, the shopkeeper shares something important. Regardless of how many products exist in the town, the total value is always the same. In other words, whatever jewels come in from customers are exchanged for products. And if a customer returns something, they get their jewels back. No shoes, cars, or jewels ever come from outside the town because it's the only place that exists. Living in this town is strange because you can tell how many jewels someone has just by looking at the height of their shoes or the speed of their car. Intrigued, the stranger decides to investigate further. After carefully measuring the height of everyone's shoes and the speed of everyone's cars, he figures out how many jewels are in circulation at any given time, both in a store stock and in a products bought by townspeople. The next day, he decides to do the calculations again, just to make sure he didn't make any mistakes. But something odd catches his attention. Some of the cars that were slower yesterday are now faster, and some of the shoes that were tall are now shorter. Although this causes a bit of confusion at first, when he adds everything up, the total number of jewels in the town is still the same. He comes to an interesting realization. Some of the people who had slower cars yesterday must have borrowed the height from other people's shoes to make their cars go faster. Meanwhile, the people with the taller shoes must have lent some of their height, which is why they're walking around with lower shoes today. In other words, they transferred the jewels from their shoes to boost the speed of their cars. Even though some cars are faster and some shoes are shorter, when he totals it all up, the number of jewels in the town hasn't changed. It seems there's something peculiar about this town, some kind of a fundamental law that the stranger didn't know about before. The total amount of jewels always stays the same, no matter what. This law operated on a principle of conserving the total number of jewels in the town. No matter what happened, the total value always remained the same. The same concept applies to the real world, but in a more complex way, to bridge the gap between this example and what happens in reality, what we call the conservation of energy. Let's break down a few key points. First, increasing the number of cars on the road decreases the number of people wearing shoes, and similarly, increasing the number of people in shoes reduces the number of people driving cars. This is the same as saying that in nature, energy can only be transferred from one form to another. It can never be created out of nothing. Second, just as we can determine the jewels invested in a shoe or a car by looking at its height or speed, in nature, we can calculate the energy of objects in various forms using mathematical expressions. These formulas help us understand energy in all its different shapes and applications. Third, we treated the town as if it were the entire universe. This was crucial because it ensured that nothing entered or left. This is a hugely important concept known as an isolated system. The conservation of energy only works if we can be sure that nothing is added or taken away from the system. The law of conservation of energy tells us that the total energy we initially calculate remains constant, even as the system changes. Energy cannot be created or destroyed, only transformed or transferred between its different forms. This law is so fundamental that, to this day, we've never seen it violated in any physical system, and that's pretty remarkable. So, we've now discussed what energy is and what it means for energy to be conserved. You might be wondering, when we say something is conserved, in relation to what is it conserved? The answer was actually hidden in our scenario. Day after day, the stranger calculated the total number of jewels in a town and found that it remained the same each time. Days, hours, weeks, seconds. These are all units of time. So when we say that the total energy of a system is conserved, we're implicitly saying that it's conserved over time. Thank you so much for watching, and I'll see you in the next video.